Banks are facing a risk problem and are aiming to reduce their current rate of default on customers. The financial crisis worldwide did not help the situation, with the number of unfulfilled loans skyrocketing. Banks need to make wise decisions and take calculated risks regarding to whom they choose to grant a loan and for which amount. Our goal is to offer the bank an effective solution. Let's go through the Lending Club dataset. Loan classification is a vital process for the banks to have a real picture of the loans issued. It helps monitor and take appropriate decisions regarding each loan account by evaluating the related financial information, credit scores, payment patterns, and loan status. The Lending Club dataset includes information for loans issued through the 2008 to 2015 period, including the current loan status as well as the latest payment information. The dataset has a lot of missing values. Actually, almost 25% of the features include more than 85% missing values. Additionally, 7% of the loans included in the dataset are default loans. Our goal is to develop a model to perform a two-class classification for the loans. Scikit Learn is a software machine learning library available for the Python programming language. It was initially developed by David Kurnapur as a Google Summer of Code project in 2007. Later, Matthew Brusher joined the project and started to use it as a part of his thesis work. In 2010, INRIA got involved and the first public release was published in late January 2010. The project now has more than 30 active contributors. Scikit-learn provides a range of supervised and unsupervised learning algorithms via a consistent interface in Python. It is also designed to interoperate with the Python numerical and scientific libraries. The library is built upon the SciPy that must be installed before you can use Scikit-learn. This stack includes NumPy, SciPy, Matplotlib, IPython, SymPy, and Pandas. Extensions or modules for SciPy are conventionally named Scikits. As such, the module provides learning algorithms and is named Scikit-learn. As a first step, we are using the Pandas library to read the CSV file and enter the data in Pandas data frames. Using the head attributes of the Pandas data frame, we can see and examine the 5 first rows of the dataset. Using the shape module, we can get the data frame's number of rows and columns respectively. Subsequently, by implementing the .columns attribute, we get the names of the columns, as they were read from the CSV file. Finally, using the .dfTypes attribute, we can obtain the type of each variable. The target variable has to be set. It is a variable named loan status. We inspect this variable and observe that there are 10 different classes in loan status, and we can see these classes here. Our goal is to reduce the problem from a multi-class one to a binary one. Is it a good loan or a bad one? Before moving to the next step, we count the values of the target variable and then plot them using the Matplotlib and Seaborn libraries. It is obvious that we have to deal with a highly imbalanced dataset, with more than 93% being zeros. Before attempting any modeling techniques, the dataset has to be prepared. First, we check whether there is any variable that has a constant value throughout the dataset. As a matter of fact, the policy code is uniform in the whole dataset, thus not adding any information. Therefore, we can remove it. Then, we remove features that exist in the dataset only for identity purposes and are not to be used during modeling. We continue by checking the number of unique values in non-scalar features. We can identify a few of them that have too many unique values to be considered valuable and remove them. Just by investigating our dataset, we have already reduced the number of features, and we are not done yet. We move to check the missing values from the dataset. We create a new data frame and fill it using an apply function, with a lambda anonymous function, an extremely efficient way to perform computation on the whole dataset, especially such a large one. Inside the anonymous function, we get the count of NAs using the .isNA attribute and summing it and dividing by the number of rows of the dataset in order to obtain a percentage. We can see that there are a lot of columns that consist almost entirely by missing value. Our decision was to remove those that consist from more than 50% of missing values. It was an arbitrary decision, but together with the feature description mentioned above, we believe that we are justified to do so. Then, using pandas advantages, we called for the rows of the created data frame that had a value larger than 0.5 and asked for their index, meaning the feature name. Again, by using the .drop attribute of pandas, we remove these columns, ending up with 45 features left. Not bad so far. We moved to create some new variables that could improve our work or transform our current ones. To begin with, we convert the employment length variable into a numerical one. We have seen at the beginning that it is read as an object by Python, and we have already seen that it has about 5% of missing values. Using .loc, we locate the rows where there is a missing value and replace it with a 0. And using the same method, we find the rows that have the value less than 1 and replace them with a 0 as well. Finally, we replace the regular expression in the rest of the column and transform them into integers. The second transformation we performed is that we took the earliest CR line variable, a date object which expresses the month the borrower's earlier reported credit line was opened, and modified it to the numerical variables CR years before loan to gain a better perspective. We take the column, and from that, using the .str.extract, we obtain the year, then locate the cells with missing values and replace them with a 0 as a string to be in order with the column type. Then we transform the whole column from string to integer. Finally, we now locate the rows where the value is 0, a value that does not make sense in the scope of what this variable expresses, and replace the 0 value with the global median, obtained using the NumPy library. To create the new feature, again, we extract the numerical values from a string using issue.str.extract. We take the first column of the return, the year part, convert it to an integer, and then subtract from that the year we calculated before. And all that in only one line. At the end, we drop some other date-related features from which we are not able to extract any helpful information. As a last step, we have to deal with the remaining missing values, since most Scikit algorithms and modules are not functional with them in place. We create an anonymous function that is applied to the data frame, where the NAs are replaced with 0 when the data type is float or integer, thus a numerical feature, and with the string none if it's a categorical feature. We repeat the same line of code we used before to count the NAs in the dataset, and indeed we are free from NAs at last. Here, for the first time, we begin using Scikit-learn's features and capabilities. In order to scale the features, we initialize Scikit-learn's standard scaler, which subtracts the mean of the column and divides by the standard deviation. We use the function we have defined to only get the numerical variables from the data frame. Then we create a for loop to parse through these numerical variables, print the initial mean, maximum, and minimum values, and then, using the .fit transform, we fit the transformer to the data, and the transformed version is returned. Finally, we print the new mean, the maximum and minimum values of each column. Now, we want to create dummy variables for our categorical ones. This is a pandas feature, getDummies, and we order to do it on the variables that it can be done, meaning the categorical ones, adding an extra argument to include the features that are labeled as an object. We add all those columns in a newly created data frame to be joined with our original dataset in a bit. We drop the variables we have dummified and join the new dummy data frame with the old one. Now we want to split the dataset in two parts, the training set and the test set. To achieve this, we use another scikit-learn feature, the train test split, with the first argument being the data frame to be split, the second one being the proportion of split, where we set a 90-10 split, and then at the end, we set the random state to be able to replicate our results in the future. Then we print the shape of the two splits, and finally we check the distribution of the target variable to see if it's representative of our original dataset. Our next goal is to balance the distribution, and to achieve that we perform downsampling. What we do here is get a data frame with all the occurrences where the target is 1 and another one where the target is 0. We randomly get the indexes from the total of the length of the data frame, without replacement. We ask to sample as many instances as the length of the data frame, with the target equaling 1. Finally, we downsample the zeros by slicing on the random indexes and append the new data frame to the one where the target is 1. Now, it's perfectly balanced. To begin with, we drop the target variable from the test and training sets, setting them as a separate pandas series. It is time to select the features to be included in our model. The 105 we have now are a lot, and of course not all of them add value to our model. One method to do that is to use scikit-learn's extra tree classifier. We initialize it and define the selector by feeding our dataset to the transformer. Then we plot the outcome in a bar plot using matplotlib, adding title and labels. Subsequently, we use the select from model, a meta transformer for selecting features based on their importance. We initialize it and feed it to our dataset both in the train and the test set. We end up with 28 features. Then we implement another scikit-learn method called recursive feature elimination, where it performs cross-validation after removing features one by one recursively and returns the subset of features that has the best cross-validation score. Let's move on to the modeling part. We are going to use a random forest classifier from scikit-learn. We initialize it inside the initialization of the grid search cross-validation, a hyperparameter tuner, again from scikit-learn, which performs a grid search evaluating each possible combination of hyperparameter values from the ones we introduced to the algorithm. In this case, we give different number of estimators, different maximum depths, just to demonstrate how the algorithm works. The number of jobs is set at -1, meaning that we are using all resources and we are scoring based on recall. Again, we implement the algorithm using .fit. We print the best parameters from the grid search and the best score that came out of these parameters, using .bestestimator and .bestscore respectively. We see here the best parameters as well as the best cross-validation score for recall at 0.81. At the end, we made the prediction using the fitted model on the test set, using the .predict. Then we print the confusion matrix to see where our model was correct and where it was not. The recall on the test set is 0.79. We are going to go through different algorithms offered in the scikit-learn environment. Here, we repeat the grid search using gradient boosting classifier this time and set some possible values of hyperparameters. The data is fed on the specific algorithm, and again we print the best set of parameters and their score. We see the confusion matrix again and print the recall score on the test set. Finally, we repeat the same procedure, this time using an ADA boosting classifier. To present our final model, we introduce the voting classifier. What the voting classifier does is that it is fed multiple different models, and the prediction of each model is its vote in the final outcome. There is a possibility to enter the argument voting equals soft, where each algorithm's probability in favor of the outcome they predicted becomes their vote. The voters are the models we introduced previously. At the beginning, we initialize the models as they were defined before and use .fit to feed our dataset exactly like before. Then we predict the outcome using .predict and examine the confusion matrix and the recall on the test set. The voting classifier did not outperform our best individual model, the ADA boost classifier. That's how a typical machine learning task is carried in Python using the scikit-learn library. Thank you for staying with us until the end.